So for today, we'll switch over to our lunch speaker, Jesse Melick. Jesse will be talking to us today about increasing accuracy of well prediction, linking reservoir bodies to charge footprint, Eastern Greater Green River Basin, Wyoming. Jesse is another awesome RMAG member who contributes a lot. With his 22 years experience as a professional geologist, he has a wealth of knowledge, especially as a sedimentologist. Jesse was in academia up until the last 9 years. He's been with BP, now BPX, working in technology organization and exploration and development. So Jesse, that's a really high level overview. I want to make sure we give you enough time to get through all of your talk. And I think folks, what we'll do today is we generally adjourn right at 1 o'clock. I know Jesse has about half an hour, which will put us right at 1. So what we might do is just, if you do have questions, you can either email Jesse. Hopefully he put his email at the end of the slides, or we'll go late by about 10 minutes or so in case anybody wants to stick around for questions. So with that, go ahead and take it away, Jesse.
All right, and you can see the screen?
Yes, we can see the screen.
All right, well, thanks, Dan and RMAG for having me. I'm super excited to share this work, and I will try to curb my enthusiasm over the beginning half because that's just the setup for the really cool stuff at the end. So this work is, this was performed 4 or 5 years ago in conjunction with one of our assets, Wyoming asset at BP. This is highly integrated geology, geophysics, and petroleum systems, who are both very talented individuals and just a pleasure to work with. Also want to thank Ron Steele's group at BEG. We had lots of, showed him this stuff and had lots of conversations with them and used quite a bit of their literature to kind of frame it, and you'll see that in there. And then thanks to BP and BPX for the permission to present. All right, so just the outline here. I'm going to talk about the GOR surprise, the asset discovered on bringing on some wells that was not in line with what they expected. That's the first little bit, and that's going to be in the Lewis Basin floor fan. That is the sand body that we're going to be talking about on the left. That's a 3D, an isopac map draped on a 3D surface, and that was bypassing a shelf on the right side of the picture, which is the Fox Hills Shelf Edge Delta out by Rollins. Then I'm going to go just to do a quick overview of petroleum, just petroleum, a couple slides on that to get people who are less familiar with it up, get the terminology out there, go through some geologic setting and depositional models, and that's the part I'll probably try to move faster through because it's a lot of literature. And then get to the fun part of defining our reservoir bodies in well logs and seismic. That's the integrated part with some really cool seismic, internally generated seismic volumes. And then ended out with the charge model and footprint and how we were much more accurate in predicting the well performance after obviously doing all this work and after the wells. But if it had been done before, bringing on wells, we could have, according to the work, been a lot more predictive in our GOR estimation. So to get started, I'm just going to set the stage here. I'll go through all the setup of the Eastern Greater Green River Basin that we're seeing here. I just want to use this focus right now on the issue that got this work started. And it's in the northern half of this map. And this is from the USGS TPS report, highlighting this is the main structural setting here, where we have a Great Divide, or Red Desert Basin in the north, Wamsutter Arch, Washakie Basin to the south. And so I just have a few animations of kind of the key structural features defining these two basins. And for this presentation, we're just going to focus on the northern part. Now, this is another image from the Petroleum Systems report. And the lines to focus on are the dashed blue or dark blue lines. That is the vitrinite reflectance values at the Asquith Shale, which is right at the base of the Lewis Shale. So that is the inferred source rock for this play. And so you can see I highlighted a 1.1 RO and a 0.8 RO just to give us a reference. And for this presentation, let's use this as the Lewis play outline. So let's just look at these two. If we were to come at this and say, what do we predict these two wells to come on as in a GOR space? Okay, so let's drill a well here at about the 1 RO and then maybe at the 0.9 RO, just for argument's sake. So this is an internally generated GOR versus RO maturity plot for this basin, for this area, by our friendly neighborhood petroleum systems analyst. And so we have the GOR values on a log scale on the right and the reflectance on the horizontal. And so what I wanted to do is just say, now let's use where those wells lined up. Can somebody please, there you go, line up. So we'll point out the 1 RO would be about a 2000 GOR is how that would be read. So let's plot our wells on there and see, okay, so the black one, which is well number 1, would be if this is, according to this, would be a 2000 GOR, and the green one, which is well 2, coming up, it would be about a 1000 GOR. So black to volatile oil would be predicted. All right, so the surprise. We came in, drilled some wells, and this is considering this is the play area. BPX has been drilling it through the Lewis for over a decade into the Almond Formation, which gave a lot of thousands, close to 10,000 wells drilled through the Lewis sandstones. So we this prompted the appraising, and I guess that's a bad word, evaluation of the Lewis tight sandstone play. So porosity is in the 8 to 14% range, and permeability's pretty good in the 1 to 500 microdarcy. So it was a gas play, considered to be a gas play, but we kept seeing oil shows as we were drilling through it. And that's, these are in this chronostrat chart that I have worked for several years, showing the almond and then at the bottom half, and then the Asquith marker, and then the eastward prograding Fox Hills, so Lance, Fox Hills, and Lewis system, and these would be the roughly the position of those Lewis sandstones. So for this talk, we're just going to talk about these 3 wells, and that's the order they were drilled, 1, 2, and 3. And there was a significantly different GOR range than was expected. And this was not predicted by their 3D dynamic modeling, and therefore they reached out to me as a deep water stratigrapher to help with their interpreting the finer layers of the sand body. So in reality, well 1, which predicted at 2000 GOR, came in at 3200, which is awesome. So amazing. That's a perfect light oil, heavy condensate. Well 2, oh my God, we got almost a wet gas. So a lot less rich condensate. And then they came in and drilled well 3, and it was somewhere in between, right? So well 3 was drilled after this work and is predicted for a different reason than it's just between those 2. All right, so why does the GOR increase up dip? If this is a resource play, shouldn't the depth be related to the RO like in our first exercise? Well, and just remember, this is from reservoir pressure. We can see that the reservoir pressure is much higher than the saturation pressure. Therefore, assume single phase hydrocarbon in the reservoir. In other words, not a gas cap. All right. So just kind of the bringing this back to the GOR per rate. So we have rate along the bottom in barrels of oil per day. And so now down the Permian, we're over 2,000. So this is not Permian, this is Lewis up in Wyoming. And so 1,000 to 1,500 is amazing. And this is really looking at the viscosity decrease upward. And this boundary is liquid to vapor. So turns out that is really the sweet spot, the Goldilocks for rate and value of a well. Again, assume the fluids are in single phase, and these sandstone reservoirs being charged vertically from the underlying shale. So those are the assumptions in this play. So let's look at the map. Again, this is that same image as the front. These are sections, 1 mile sections across here. And so the original modeled area was in this kind of sideways house looking thing. And the first well was drilled in the middle of it. And this second well was quite a ways up, well, less than 3 miles, but outside of the model. So the idea was, well, let's, add some layers to the model and get it to predict the GOR changes. And so that's where I came in and said, okay, let's understand this depositional system and look for some compartmentalization within that large gross sand body. So those are, that's the gross sand thickness with the gamma ray cutoff. And so there's got to be some smaller bodies in there. Okay, so let's do a little overview of petroleum. I'll be brief because I assume that most know this, but I just want to hit on a few points and just kind of set this out there so we all have a feel for it and we're not leaving anybody behind. Again, to reiterate, this is the sweet spot right in this condensate between the volatile oil and condensate window, where value is usually increases with the oil rate and mobility increases with the gas component. So we're always trying to balance that in the value space. Just a couple images here for fun. An 800 GOR will be greatly appreciated at the end of the day today. We'll probably wait for a 3,200 GOR for, I don't know, Christmas or New Year's. And out in Oregon and California, they're wishing for some 30,000 GOR to help with the forest fires. So just some visual images there of gas. So gas in the liquid is a lot lower. In this lower GOR, it's highly volatile and explosive. So there's your rate and your drive inside as that's expanding and the gas is pushing the expansion. And then this would be your dry gas up here. Okay, so back to the value. Just kind of want to throw some bullet points out there. Again, try to get through this part a little quicker. Said most of all this stuff, just want to give another little image of that. So this here is a workflow for estimating instantaneous. So we're going to talk about two different types of GOR, instantaneous and and then we'll talk about the cumulative later. But to get instantaneous, you go through your expulsion rate, and this is all for the area from internal petroleum systems analysis. And you do your burial history to get the deepest the source rock was. In this case, it's that black. So the Asquith, the black down into here. And so you would assume that the RO would be, in this particular well, would be in this dry gas window down here. Okay, and then take that back to the instantaneous plot and you build this, this prediction. So let's think about cumulative GOR. So instantaneous is as you sink and you bury the source rock. Maturity, it's the the highest maturity it ever got to is that's the maturity and the GOR expected. However, when you're talking about migration, so a little more conventional charge and conventional trapping, the GOR ends up being cumulative. And what that means is that you kind of think about it as, you know, in these different ranges. So in the oil GOR range, as you're burying, you are increasing the GOR through time. So you start with say a 500, and then you're charging it up with a 2,000, a 3,000, and your cumulative GOR ends up being 1,000, for example. Now you're down into the condensate, you start off with 2,000, 5,000, 15,000, and you end up maybe with an 8,000 GOR. And likewise for once you're burying it on down. Now 60,000, maybe that's your instantaneous GOR, but the cumulative would be lower, the 15,000. So that's really the highest GOR we expected from the modeling in this area. All right, so just to kind of bring it full circle, and in this section, let's add another concept, the reservoir footprint. So this is not necessarily an undercharged system, but not overcharged. So meaning that as the source rock is being buried and it's at higher GOR, expelling higher and higher GORs, the footprint of the sandstone right above it will be that's the sum of the cumulative GOR. And then this one, so this would actually be a little lower GOR. And then maybe this one's even lower. And if we're up here in the light oil realm, then they would all be charged with oil and no gas at all. So that's kind of that cumulative and footprint concept. So let's go now to the geologic setting. I'm going to try to speed up because it's too much fun. All right, so I'll just lay this all out real quick. I'm going to go through the basin formation, the basin geometry, stratigraphic framework. We're talking the Ullmann and the Lewis. Transport from the north to south along shelf edge deltas. You saw one of those in the first slide. Use some literature to get the large scale boundaries, but really need to get into seismic at the bottom, seismic data to resolve the boundaries between some of those reservoir bodies. Okay, so who doesn't love a Blakey? So we're on the west coast of, and that took a long time to find this one. There's hardly ever show that embayment. So we got the embayment, the eastern Greater Green River Basin with that east to west shoreline. And so this is really documenting the overlap of the severe thin skin and the laramide thick skin, where you get these fold and thrust belts developing, but then also you get the basement faults that are really segmenting our basin. So folds and faults and stratigraphy and sea level and all that fun stuff. Whoever's worked Wyoming has come to love. So a quick, here's the reference at the bottom, so you can go look this up. It's a recent Mountain G publication, nicely done. And really the point I wanted to bring up here is that anything below your highest carrier bed, or the closest carrier bed to your area, is the one. Anything below that doesn't matter. Assume it's all been migrated out of the basin. So don't worry about that. Now let's look in a cross section here. And so we're really going to be looking, okay, above the Erickson in the outer eastern Greater Green River Basin where the Ullmann and Lewis were deposited. Okay, continuing on, there's that strat chart again, and with the biostrat control from Cobbin et al. And so I've gone and taken this Devlin et al. Paper, and in their paper they have this the Lewis and the Erickson, but I went and added the Ullmann in here. So just to show that this was filling in as uplift was happening on the Rock Springs uplift. The Rollins uplift was not as significant since you can correlate some of these packages farther out across Wyoming. But we're really going to be looking at this basin up in here. We're looking strike view. All the deposits are coming towards us. Okay, so there's that basin again, same as the first. Here's up on the upper, in this right side here, this is modified from Rayler 98. Yeah, nice publications there. And so I added this delta in here because we need a delta to make a shoreline to build out, and this whole basin fills through this stratigraphic the sequence of cliniforms. And these are at a little bit higher, larger scale than we'll be looking at. Ours is down in here. It's like one of these parasequence sets, you could call them. And so it's really nice looking at this in cross section because they pretty easy to correlate these scale boundaries. And so what are the dimensions of the actual reservoirs? There's your reservoir zone in here, but what are the actual bodies that are going to be charged and drained separately or charged separately based on that footprint concept? Thanks to Ron, he sent me a high resolution shot of this outcrop. It's a beautiful shelf sands with overlying coastal plain and slope sands and channels, and then basin floor fans and lobes down in here with their constituent names from this area. So notice the scale down here. This is basically just two of these little guys down in here, and so that's what that outcrop is showing. Okay, so starting to wrap up the depositional setting. Back to that Rayler depositional environment map. I'm going to look at the deltaic system, and this is all work that I did on each of those. You can see this, the parasequence sets kind of transparently overlapping each other and migrating southward. And then using the work from the steel group, they found the exact same thing. They found thin intervals on the shelf, but thick fans, and inferring these sediment fairways along the shelf into the basin. I like to go and find a modern analog. So this is Mexico, just north of Puerto Vallarta, almost to Mazatlan. And I took the liberty of drafting the environments over top of it. And I think it's a really similar scale. So that white box is the box of the study. And we see all those same elements. I added those basin floor fans, but I doubt they're there. You do see a little bit of a channel here, so there's quite something down there. So this kind of a summary, pulling core descriptions together of the cartoons, the depositional model. I generated this here based on some different core descriptions and some ideas internally. Looked at these correlations in the fine scale and their good facies and poor facies, and then in map view. So all of that needs to be integrated with the petroleum system. All right, so now back to remind you all what the problem was. We were looking at these fine layers. Okay, so the bold, the dashed, and these bold are the modeling layers, roughly, right? So this whole interval, that's the mapped interval in the dashed. And I was asked to add these fine layers. If anybody's worked deep water, you know that in an outcrop, you can see bodies correlating at high angles and pinching out in short distances. So I got to the point where I was saying, you know, guys, we're gonna need to do something different here, and we need to look at some seismic, looking at seismic for some compartments. Okay, so now for the fun part. All right, now this is working with a really talented young seismic analyst at BP, and our internal reprocessing workflows to generate some spectral decomposition volumes. And so I'll give you my email at the end. If you have questions, send me an email. I'll do my best to get you an answer that I am probably not going to be able to answer if asked here. So this is now, we went through, and in their process, they broke down many different frequencies. And so this is, what I'll do is I'll just kind of go through. There's from 14 hertz, I went in and mapped what I thought was, and this is also using it's color inversion. So the light colors in here are softer, and the blue out here are harder rocks. And so softer generally means porosity and sand and such. So I thought, okay, let's just let's just map that and see what it looks like. And then in multiple different frequencies. So there's 24 hertz, there's 30 hertz. And so the hatchered on there are the composite. So then I pulled it all together on about the 30 hertz seemed to be the best. But I used all the frequencies, those 3 frequencies, to develop these 3 polygons. Now these are, think of them as a depot center. There's still going to be a fringe overlap. So it's not necessarily, there's no sand here, but this will be your northwest reservoir, southeast reservoir, etc. And so each of those frequencies kind of picked up on a different log motif, and that would really helped in generating a, so there's our 3 wells. Now you're starting to see, okay, there's the first one's in a totally separate polygon or sand body than the second well. And I referenced that this 3rd well was in between the 2 GORs for, I believe, because there's overlap of this lower GOR and higher GOR polygon. So in cross section, this is the color inverted full spectrum volume. And so here's the almond down in here. You can see the shales are hard, sands are bright, warm, and this bright down here is that sand body we were talking about. Silts above it, and then some Fox Hills shelfal sands above it. And the point is in this is that you can see, if you squint, you can kind of see there's brights over here, bright red, and then it goes dim, and then a big bright red there. So even in cross section, you can see that this is the trace of the section in white. Even in cross section, you can see a dim that is picked up also in the different frequencies, helping to identify a boundary between one sand body and another. So we were super psyched about that. And there's the wells for reference, low GOR and the big bright sand body, a gassier well in the less bright, and then in between the 2 you have evidently had contribution from both. So let's take off the seismic and show you just kind of how that would look. If you were to try to do this in well log correlation, you probably would not ever do that. And that, it was one of those, you kind of had to force it down there because the seismic said it did, and the reservoir production, the reservoir modeling didn't predict that. Your well's production GOR did help with that assessment. So again, wells 1, 2, and 3, it's all kind of aligning. And so I took it one step further and put together a depositional model. When it went back in well logs and correlated these bodies in well log to force those 3 bodies. And this is the net sand map resulting. Depositional model from that. So shelf sands feeding these slope. They're looking kind of like they're on a ramp. They weren't fully defined. They had lots of slumps in places, and so assumed it was kind of on the ramp or base of slope. Again, there's those. And now let's get in the last 5 minutes, I was told, go through this. Remember the footprint story? So now let's go and take, I think I've only got a couple slides left, so we're going to make it. Here's the, this is our Fox Hills footprint. So this is outlined in Trinity. And this is our big polygon from the sand body from the first slide. And here are the 3 individual polygons. So I gave all 3 of these to the petroleum systems analyst. And he came in and assessed, okay, so around in that blue polygon, right? And these blue, those are roughly where the sand bodies are. So zooming in on that, this prediction, it would have said well 1 would have given a 3,500 GOR. Well 2, those are backwards, sorry. Well 2 would be the 8,100, the 8,100 is in the middle. 60,000 would have been predicted up here. You see how, okay. These are per polygon. So polygon 1, the whole, okay, right. If you take the whole polygon and give the cumulative GOR expected, it would be 3,500. Polygon 2 is this one at 8,100. And then polygon 3 up here is the 60,000. You can see how it's a lot higher GOR in this part of the fetch. So assuming it's fully mixed for the blue footprints, we come back in and say, get to the prediction, and there we go. All right, I have the answer in here. So there they are, the bodies defined, broken into 3. There's the actual GOR. We got to get to the predicted. There's the predicted. So we had a very similar prediction to actual production, and the actual values went away. Anyway, it was extremely similar, and so in the end, basin history is key. Depositional systems help identify the transport direction, what type of shingling to expect. Production is how the reservoirs talk to you and tell you their secrets. Depositional model with 3 iterations help explain that performance. Petroleum systems charge model, cumulative, and reservoir footprint really helped with this. And along the way, I learned a couple things, a couple takeaways here of be open to new data, be open to new approaches, and iterate with production data and other disciplines. And that's what I got.
All right, thank you, Jesse. And notice everybody that Jesse's email is up there at the top too, if you have any follow-up questions. For right now, I know we're right at clock. We had right at 1 o'clock. We had a lot to go over today, and thank you to Peter for all of the RMS APG awards. Thanks to Jesse for presenting this wonderful presentation today. Jesse said he's got about 10 minutes to be able to stick around and answer any questions. So if anybody has anything, please put it in the chat, or it seems like people have the ability to unmute themselves. So if you have a question, go ahead and go for it. Jesse, I'll kick it off with just a quick, maybe a comment walking through this. It really seemed like when you started to include the seismic is what really seemed to help illuminate the differences between the different geobodies. And can you speak to that a little bit more? And it's always difficult to interpret seismic, especially when you see those continuous reflectors that just may have just a little bit of dimming in the reflectivity. I mean, it's difficult to really draw that line across different bodies. Can you just comment on that a little bit?
Sure. So having done a lot of outcrop work, seen different systems in West Texas, the Bresci Canyon, Ainsa system out in Spain, rocks in Italy and around the U.S. You just know that they have a geometry that is not miles and miles. And so when the wells production has that kind of surprise, I knew there had to be something. So I basically there's got to be something in there. And you knew that the well logs are their best vertical resolution, from a well, but there are points across across your acreage in your field. Whereas seismic, even though it's lower resolution, it is a 3D volume. So it's gonna show variations, and I'm always looking for the subtlest variations to help kind of iterate an interpretation and identify some kind of potential boundary. Then when we did the petroleum systems and started getting those predictions, so close to in petroleum systems world, those, predicting a 3,500 and getting a 3,200, that's almost, uncannily similar. And same with the gassier polygon. So that really kind of brought it all together. And so kind of throw out a hypothesis. Yeah, I see, there's got to be something. I'm looking in the seismic. I'm seeing pretty convincing trends. And so just kind of go at it and be open to whatever the data may tell you, with kind of a pointed going after, there's got to be something here. Does that help?
Yeah, it absolutely makes sense as far as the theory and methodology behind why you would do that. It's just it's an interpretation, right? You got to kind of jump off the ledge a little bit and feel comfortable making that interpretation. That's always the hardest part.
Yeah, and the work that the BP folks did on the reprocessing and spec D on that volume was just amazing. For onshore seismic, it's just like you couldn't hope for better. I mean, it was pretty convincing when I showed you that cross section of with the wells on it. This is what we're seeing. This is real.
Yeah, thank you very much. Anybody else? Questions?
Yeah. Hey, Jesse, Jeff May here.
Hey, Jeff. How you doing?
Okay. Hey, I've got a question for you. Did you try instantaneous phase on your 3D volume to look at the breaks between those different geobodies, between the different fans?
I want to say yes. I was sitting side by side with the spectral analyst, the geophysical analyst, and his mentor for 6 to 8 months, and we would cycle through those different frequency volumes, and the instantaneous phase sounds like we need to maybe get a beer and talk about it. I'm open to learning more about it. I'm not a geophysicist at all. I try to remember as much as I can about our conversations, but
Yeah, we found when I was doing some work for when it was still Enron Oil and Gas, that kind of dates me. I was doing geophysical interpretation, and we could separate out separate fan lobes using instantaneous phase, where if you just had the well logs, or if you had impedance volume, or even frequency volumes, it looked like the same sand body. But instead, you could see the breaks, and you'd have different production characteristics in the different wells, and you'd have different amounts of water versus oil. So this was in the God, I can't remember, in the San Joaquin Basin, the Stevens sandstones out there. So it was really interesting, and that was actually something Rob Sterling pointed out to me to try. So it was just instantaneous phase will sometimes show you the separations between the different sand lobes or the different fan bodies.
cool. I'll keep that in mind. I'm trying to do a similar thing in the Bone Spring of Delaware Basin. So I'll throw that at the geophysicist and see if that's something we can look at. Thanks, Jeff. Good to see you.
Thanks. Good seeing you.
Hello, this is Paul Lillis. Can you hear me?
Yep. Hi, Paul.
I have a question about kerogen. Gas oil ratio is dependent upon kerogen type. Did you look at the relative contributions of type 2 versus type 3 kerogen as you move laterally between wells?
That's a good question. Yes, we had the more gas-prone kerogen. Again, I'm not a petroleum systems expert, so I'll talk the way I know. And so the gas-prone kerogens were in the Almond and the Fox Hills and Lance. And then the more oil-prone were associated with the Lewis. So turns out we saw a lot more of the oil-prone signatures in the Lewis sands. So that suggests that there was a lot more charge from the Asquith Shale as opposed to the Almond. Previously, we had thought the Almond charged everything. But in those lower GORs, there had to be another oily prone source, and that's what we came up with. Does that answer your question?
Partially, but also just within the Lewis, you could have variations in the kerogen type going from distal to proximal.
So I understand. Yeah, I see your point. So this study was just in that area. It was, 15 square miles, one sand body with multiple lobes in it. And then we put Wamsutter on the market. So if you're interested, you could buy Wamsutter and do some sampling. No, I don't have information. There may be some variations in oil types and oil signatures around, but that's kind of beyond my knowledge. Sorry.
All right, thank you.
Yeah. So I've already gotten an email or two. I think we'll just go with that. I have another presentation that started 8 minutes ago and after that. So it's a presentation day for me.
All right, Jesse. Well, listen, thank you very much. Really appreciate it. And thank you everybody for being here. And we'll see you again next month.
Thanks so much. Thanks,
Well,
Dan, for announcing. Thank you so
Always.
much.